So I think first it helps to state what a compound angle actually is. So for example, sine x, the angle x isn't compound, it's not a compound expression. What makes it compound is if it's, for example, something just a bit more complicated than x. So for example, sine of x plus 90 would be compound because an expression, it's a linear expression, more complicated than just x. And we're going to have a look now at how we actually expand brackets like this, because in trig it's not the case that that is just sine x plus sine 90. So the actual formulae that are in your formula book, and we won't prove these, there's a nice animation online that I can point in the direction of. I'll put a link on the lesson archive area that you can go to for that. There's a nice animation that proves these identities, but I'm just for now going to show you exactly how they expand. So, whenever you've got an angle sine of A plus or minus B, that's how it expands there. So if you choose plus here, if it's A plus B, then this is a plus. If you choose minus, this is a minus. It's the opposite way around for cos. So cos of A plus or minus B. Well, if you choose plus here, the top one, you choose minus there, that's a minus or plus. So that's the significance of that. If you choose that there, minus, then you choose plus there, and there's tan. So this is given in your formula sheet. You don't need to remember these. So let's do a quick example. E.g., expand sine of 90, sine of theta minus pi over 2. So using those formula there. So in this formula, A is theta and B is pi over 2, and we're going to use the subtract formula. So take a moment and have a go at that. And I'll quietly get on with it so you can check your answer. So we're not quite finished yet, because the values of cos of pi over 2 and sine of pi over 2 are easy to calculate. You can either chuck it in your calculator or just recognise what it's going to be from just knowing the shape of the graph. So this one here, cos of pi over 2 equals 0, and sine of pi over 2 equals 1. So equals minus cos theta. Let's try and make mathematical sense of this using the graph of minus cos theta. So the graph of minus cos theta so the graph of positive cos theta roughly looks like that. So minus cos theta will be reflected in the x-axis like that. Let's now have a look at the graph of, let's put on there the graph of sine theta as well. So sine theta, like that. And this here, this graph here, we'll continue it a bit down there as well. So this graph here would be sine theta translated pi over 2 to the right. So if we do that, if we translate each section of this pi over 2 to the right, we see that we translate it that way. So actually, this bit's going to end up on there, this bit's going to end up on there. It's the same graph. So we've just proved using a different method, using compound angle formulae, that sine of theta minus pi over 2 is equal to minus cos theta. So we proved it one way using compound angle formulae, the other way using the graph. So let's try another. E.g., expand tan, we'll do this in degrees, of theta plus 180 degrees. So see if you can expand that using the tan formula, which I'll just put next to it for ease of use. So have a go at that. So this is A, this is B, and notice the minus or plus there rather than plus or minus. So if we choose the top sign, which is plus here, we choose all the top signs here. And notice that we can easily find out the value of tan 180, which just comes from knowing the graph or using a calculator. Tan 180 is 0. So that term disappears, as does that one. Just giving tan theta itself. So tan of theta plus 180 is tan theta. Well, we knew that because we knew the period of the tan graph is 180. So we haven't really proved anything new there. We've just verified that the tan graph has a period of 180 degrees, or in radians, pi. So there's nothing new that we're finding out here, other than how to use the trig formulae. So let's have a look at an example question that you might be asked in using these formulae. So it's saying express each of the following in the form sine alpha, where alpha is acute. So this time it's about working backwards. It's told us to use the sine formula, which is there. What's asking you just to write it as sine of an angle. So combine this into a single expression only involving sine. Take a moment to do that. See if you can work backwards. So one thing I'm noticing here is that in the formula, that's A, that's B, A and B, and it's a plus in the middle. So when it's in this form, which it is, it's just sine of A plus B. So sine of 10 plus 30, which is sine 40, and indeed the angle alpha, 40, is acute. Try B. But notice that the angle, notice that the sine in the middle is a minus this time. So we're going to use sine of A minus B. Sine of 67 minus 18. Which is sine of 49. So nice and straightforward. Let's do another. So expresses a single trigonometric ratio. So first of all, you've got to recognize which of the formulae it relates to. So this one is cos cos, sine sine. Well, looking at your formula sheet, you'll realize that this is the one here to use. Cos cos, sine sine, with a minus in the middle. Cos cos, sine sine. And the minus here is at the top. So we're going to use the top sign here as well. So top sign and top sign. So cos of A plus B. So we're going to add the angles together. Makes it cos of A plus 2A equals cos of 3A. The second one, sine cos, cos sine. Compare it to the formula you've got. And you'll see that it's this one here. Sine cos, cos sine. And there's a minus in the middle. So we're going to use the bottom sign here, which means we use the bottom sign there as well. So that's sine of A minus B. So that becomes sine of 4A minus B. So expanding angles, just be vigilant. When you're asked to expand angles, it's dead easy to forget and try and do something like that, but that's not the case. As I say, if you want to see the proof of this, I'll put in the on the lesson archive section a link to animation that does prove them. But it's quite time consuming, so I'll leave you to do that in your own time. Right, let's try another one. And just developing on the types of problem that we could be asked with this. Another type of question that could be asked is something like this. So again, it's taking the expanded version and working back to a compound angle. So find the maximum value each expression can take and the smallest positive value of x in degrees for which the maximum occurs. So cos cos, sine sine with a plus in the middle. We know that that will go back into compound angle format as cos of x minus 30, looking at your formula sheet. So it's asked for the maximum value that this function can take. Now that it's in compound angle format, it's much easier to deal with, because I can see that this is just cos of something. Well, I know the maximum of any function that starts just cos is 1. So the maximum value is 1. So just had a question, do we need to memorise these? No, these are all in the formula sheet. Depending on your exam board, they're either in a separate formula sheet that you're given in an exam, or they're given at the front of an exam paper. So in OCR, they're given to you in the front of the paper. In Edexcel, they're given as a separate formula sheet. So cos of x minus 30, the maximum of that is 1, the maximum of cos function is 1, and the maximum of cos occurs when this angle is 0. Let's just show what I mean by that. The maximum of cos happens there, happens at 360 or 2 pi. In fact, it happens in cycles of 360. So we want that angle, x minus 30, to equal 0, which means that x equals 30 is the smallest positive value for which that maximum occurs. So there's our answer there, and there's our answer there, the maximum and the smallest positive value for which it occurs. See if you can do something similar with part B. Take a moment. So that can be written as, if we take out a factor of 3, sine x cos 45 plus cos x sine 45. And look at the formula sheet, we can see sine cos, cos sine. That would be the sine compound angle, and it's a plus, so that would be 3 sine of x plus 45. So we know that that has maximum. Well, the sine function normally has maximum 1, but we can see here this 3 has stretched it by scale factor 3 parallel to the y-axis. So the maximum now is 3, not 1. And the smallest positive value of x for which the maximum occurs, well, the maximum of sine happens at 90 degrees or pi over 2. We're talking in degrees here, so 90 degrees is where the maximum of sine happens. So we want this angle here to be 90. That's where the maximum of sine occurs. So x plus 45 equals 90, which means that x equals 45 degrees. Like that. So there's a few questions like that on the worksheet that I've put in the lessons area. I just want to now have a look at some different scenarios that you might be given in trying to solve equations involving this. And the key when trying to solve equations is knowing when to expand the compound angles or when to put it back in compound angle form. So I'm going to give a few equations. All of these are from the worksheet that I've put up. So solve each equation for theta in the interval 0 to 360. So degrees, given your answer, to one decimal place where appropriate. So we'll just go through a few of these different questions that you could be asked. One second, I'm having trouble moving that. There we go. So that one there. So you've got to decide whether it needs to be expanded or whether it needs to be put back in a compound angle form. I think this one's a little bit more obvious because we can see clearly it's already been expanded. It's quite a difficult equation to solve as it is, so maybe would benefit from putting it back into compound angle form. We can see it's sine cos, cos sine. So if you have a look at the formula, the one that it's most similar to is this one here. So use that formula to put it back into compound angle form. And once it's in compound angle form, it's much easier to solve. So that becomes sine of theta plus 15 equals 0.4. And that's now much more like one that we would be asked to solve when we first started off doing trig. So now we can inverse sine both sides, but remember, it wants all the answers from 0 to 360. Here, we're currently solving not for theta, but for theta plus 15. So all of our solutions we're going to find are for theta plus 15. So we need to add 15 to both limits. So 375 and 15 are our limits for what we're actually solving now. So inverse sine both sides, we get theta plus 15 equals 0.4. Arc sine, so arc sine 0.4. Like that. And let's work that out on a calculator. Make sure it's in degrees because the actual question's in degrees as well. So put the calculator in degrees mode, shift, setup, angle unit degree, and arc sine of 0.4 is 23.578. So I want my answer to be correct to at least 3 significant figures, so I'm going a few more than that. I'm going 5 significant figures currently. But there's loads of other answers as well, potentially. So what we're going to do, we're going to draw the sine graph now. And see potentially where those other answers are. So we want all the way from 15 to 375. Well, we'll start at 0 just because it's easier to draw that way. 0, 90, 180, 270, 360, then a little bit more added on to take us past, up to and a little bit past 375. So 0, 90, 180, 270, 360 and 450. Remembering we only want solutions between 15 and 375. And this isn't the theta axis anymore. It's actually we can think of it as the theta plus 15 axis, because all of these are values of theta plus 15. Right, so we wanted where sine of theta plus 15 is equal to 0.4. So let's draw a line horizontally, roughly at 0.4. And the potential solutions we've got are here, here, and here potentially 3 solutions. So the first solution, well, if we're starting at the top of the hill, at the start of the graph rather, the bottom of the hill here, that's the very start of the graph starts at the bottom of the hill, and we have to walk 23.578 to get to the first solution. Starting at the bottom of the hill at that side, we're going to have to again walk the same distance, but this time to the left. So it's 180 minus 23.578. Move those up a little bit for tidiness. And then, again from the bottom of the hill, we're going to have to walk again 23.578 to the right. Clearly that's going to take us out of the limit's 375, so we're just going to disregard that answer. We know we've got the 2 answers we need. So theta plus 15 equals 23.578, and 180 minus that is 156.422. And remember, we need to take 15 from each of those. Those are solutions for theta plus 15. Therefore, theta equals 23.578, take 15, 8.578, and 156.422. Take away 15 is 141.422. So 4 significant figures for both answers there. Usually the exam boards require at least 3, so I'm going a little bit more than that to make sure I get the marks for accuracy. So that's how to solve one of those. Let's have a look at another question. Let's see how they can further develop it. So I missed a question out. I'll go to part C on this worksheet now. So remember, the limits are still 0 to 360 from the original question. So I'll just remind us of that. 0 less than or equal to theta less than or equal to 360 degrees. So looking at this one, we either have to expand or to put in compound format. Well, I can see it's already in compound format. So I think the most sensible thing here to do is to expand that using the formula. So let's get the relevant formula back. It's a cos expansion. So that's the relevant formula to use. So see if you can do that. Take a moment to expand it and see where that goes. Okay, so expanding that, we'll get cos theta, cos 60. And it's the minus here, so that means there's going to be a plus here. Plus sine theta, sine 60 equals sine of theta. Cos of 60 is 1/2, which means that 1/2 cos theta plus and sine 60 root 3 over 2 sine theta equals sine theta. So notice I've got a mixture of sines and coses there. Well, this is an ideal opportunity to turn something into tan. Remembering your trig identities from the first year, we know that tan theta is identical to sine theta over cos theta. So if I divide both sides by cos theta, I get, well, divide that term by cos theta, I get a half. Divide this term by cos theta, it becomes tan theta equals, again, sine theta over cos theta is tan theta. So we'll keep going like that, which implies, let's get all the tan thetas on one side now. So a half equals tan theta, take root 3 over 2 tan theta. Let's get all the tan thetas in one place now, which means that 1/2 equals, if we factorize out the tan theta, we get 1 minus root 3 over 2 dividing by that number, dividing by 1 minus root 3 over 2. We get 1/2 over 1 minus root 3 over 2 equals tan theta. And we could try and simplify that. In fact, let's do it. The calculator will do that for us though. So 1/2 over 1 minus root 3 over 2. And let's see if it gives us a nice number. It does. It gives us 2 plus root 3. And now we're charged with just finding the solutions to tan theta equals 2 plus root 3, which again is a question like it could have been given in first year A-level maths. So have a go at that. Take a moment. I'll do my answer in a second. So theta is the arctan of 2 plus root 3, which is 75 degrees. So arctan of 2 plus root 3 equals 75 degrees. And the period of the tan graph is 180. Not a particularly good tan graph, but we can live with it. 75 and 75 plus 180. Should be able to do that in my head, but I don't want to take any risks. 255 degrees, and that's it. So there's our two answers. Be careful of a different type of one that I can throw at you. This one here that I'm about to put on screen. Don't be confused by the fact that it's got a 2 theta in it, and don't feel that we need to do anything about it until later. So, naught less than or equal to x less than or equal to 360, again, is what we're solving it for. So expand that, except this time, our A is 2 theta, and our B is 60. Here, A 2 theta again, B is 30. making sure you choose the appropriate formulae. Put the identities there just so you can see them. Have a go at that. I'll start it in a moment. I'll give you a chance to get a little bit of a head start. So expanding the first one, we'll get 3 lots of cos 2 theta cos 60 minus sine 2 theta sine 60. Then we're going to take sine 2 theta cos 60. Take, so it was cos 30. Take cos 2 theta sine 30, like that. So again, we know the value of cos 60. We can just get straight from the calculator. Cos 60 is a half, so equals 3 lots of 1/2 cos 2 theta minus root 3/2, which is the value of sine 60 sine 2 theta. Take so cos 30 is the same as sine 60, so root 3/2 sine 2 theta minus 1/2 cos 2 theta. And let's expand those brackets now, which is equal to 3/2 cos 2 theta minus 3 root 3/2 sine 2 theta minus root 3/2 sine 2 theta, double minus, so plus 1/2 cos 2 theta. So keep simplifying that. I'll give you a moment again and come up with an equation to solve. So we want to solve this when it's equal to 0, as the question tells us. So each of these lines is equal to 0. So really more appropriate will be using the implies sign at the front. So 3/2 cos 2 theta plus 1/2 cos 2 theta. That's 2 cos 2 theta. Minus, and 3 root 3/2. Or minus 3 root 3/2 sine 2 theta minus root 3/2. That's 4 root 3/2, or 2 root 3 sine 2 theta equals 0. And again, it's one of those that's going to boil down to tan. So if I divide everything now by cos of 2 theta, 2 minus 2 root 3 tan theta equals 0. tan of 2 theta rather, divide everything by cos of 2 theta, I get 2 minus 2 root 3 tan of 2 theta equals 0. Which means that 2 root 3 tan of 2 theta equals 2. Which means that tan of 2 theta equals 2 over 2 root 3. And remember, we need to solve that for 0 less than or equal to theta less than or equal to 360. But we're currently solving this for 2 theta. So we need to double everything. So the limits are doubled. So finding our first solution, 2 theta equals, it's the arctan of 2 over 2 root 3. So arctan of 2 over 2 root 3 which is 30 degrees. And drawing the tan graph, or you can just remember that it has a period of 180, but we need to do it for all the way from 0, not to 360 anymore, but up to 720, because the limits have been doubled. So the tan graph, like that. So 0, 90, 180, 270, 360, 450, 540, 630, and 720. So we can see we've got a number of solutions there. So first one's at 30 degrees. Second 180 plus 30, 360 plus 30, 540 plus 30. So the solutions are 30, 210, 390, and 570 for 2 theta. So halving each of those. So 15 degrees, 105 degrees. Should know this, but again, I'm not taking any risks with it. Mental arithmetic, 195 degrees. And in an exam, when you're under pressure, no point in putting yourself under any more undue pressure by trying to do arithmetic in your head. And there's all the solutions there. So again, the worksheet has loads of examples of this. You should try and have a go at them all. So I want to move on now, after that, onto double angles. So a double angle is just what it says. It's an angle that's been doubled. So for example, cos of 2 theta is an example of a double angle because it's an angle theta that's been doubled. Now what we can do, we can expand these angles by rewriting it as cos of theta plus theta. So hopefully you're convinced that theta plus theta is 2 theta. And we can expand these using the compound angle formulae as per your formula sheet. And this is the cos one. So it's like that. So try and expand that using that formula where A is theta and B is also theta. So we get cos theta minus sine theta sine theta, which is cos squared theta minus sine squared theta. Using a similar method, and the sine formula, we can derive another double angle formula for sine. So see if you can do that one yourself. Like that there. So now I'm going to do a little bit of a summary without proof of the formulae that you need to know. So we need to remember that sine theta, a sine of 2 theta, equals 2 sine theta cos theta. We need to remember that cos of 2 theta, as we did prove above, is cos squared theta minus sine squared theta. But if we use the trig identity that we derived, that we learnt in first year, i.e. cos squared theta equals 1 minus sine squared theta, we'll see that this could be also equal to 1 minus 2 sine squared theta. And if we turn this instead into 1 minus cos squared theta, we get 2 cos squared theta minus 1. And you have to remember all three of those, as well as the sine one. And you also need to remember the one for tan, which you can prove a similar way to the way we did for sine and cos. So tan of 2 theta equals 2 tan theta over 1 minus tan squared theta. Again, all of these need to be learnt and remembered. There we go. And the best way to learn them is by doing questions on them and write them out each time you do a question on them. Not just by sitting memorizing formula sheets. Actually do questions and write them out. And that way you're both learning the formulae and practicing using them, which is far better than just sitting learning a formula sheet. So let's do an example. Of using these double angle formulae. So solve each equation in the interval 0 to 360, give your answers to one decimal place where appropriate. So this one here, cos of 2x plus cos x equals 0. So what we need to do is expand the double angle cos of 2x. But you've got to figure out which of these three expansions actually is the most useful. Well, I'm going to say the third one is the most useful here. Cos of 2x is 2 cos squared x minus 1, because we end up with just an expression with cos x in it, which is what we want. We want to be able to solve it. So expanding cos of 2x to get 2 cos squared x minus 1 plus cos x equals 0. And now we've got a quadratic to solve. I'll make that look a little bit more like a quadratic by writing the terms in an order that we'd expect. And see now that we've made it look like something we're more used to solving, it's more doable. Have a go at that, see if you can get it done. Give you a few minutes on it. And just seen by symmetry where the other solutions are. Our first solution was at 60 because of the symmetry of the graph. So this is one where we start the graph at the top of the hill, so everything relates to the top of the hill. So we walk 60 degrees to get the first solution. So we do the same to get the second solution, but we walk in the opposite direction by the symmetry of the graph. So putting the answers in order, we've got 60, 180, and 360. Take away 60 is 300. And there's our solutions to that. So another. That one there. Again, remembering that I wanted all the solutions from 0 less than or equal to x less than or equal to 360. So see if we can have a go at that one. Again, I'll give you a couple of minutes before I start, and I'll walk you through how I would do it. Okay, so the first thing I would do would be to expand the sine 2x. And again, you just need to remember these. 2 sine x cos x is the expansion of sine 2x. Plus cos x equals 0. This line I'm about to write now is wrong. The line I'm about to write is wrong. So I've noticed I can divide everything by cos x. So I'm going to do that. 2 sine x plus 1 equals 0. Then I can solve for that. Not true. When I divide by cos x, which was the wrong thing to do, when I divide by anything, I'm making a bold statement that it can never ever equal 0. Or that at least that equaling 0 isn't a solution in this equation. So for example, x squared minus x equals 0. I can just divide by x to get x equals 1, which is a solution. However, by dividing by x, I've made a statement. I am certain that x equals 0 isn't a solution to this equation, because we can't divide by 0. Well, actually, x equals 0 is a solution to this equation. So by dividing by x, I've lost that solution. What I should have done was factorised, and that way I get both the 0 solution and the x equals 1 solution. So dividing by something, when that thing equal to 0 is a solution to the equation, is a bad thing to do. We shouldn't have divided by cos x there. We should have factorised, because cos x equals 0 is a solution. So they've both got a cos x in common. So we factorise it, we don't lose any solutions. So 2 sine x plus 1 equals 0. And now we can find two solutions. We get cos x equals 0 and 2 sine x plus 1 equals 0. Two separate equations to solve, both of which are like trig that you would have been introduced to last year. So both of these are very doable. So finish off by solving those. So cos x equals 0. If you know your cos graph, you know that's equal to 0 at 90 and 270. And sine x equals minus 1/2. So if we arc sine minus 1/2, get minus 30 degrees. And let's draw the sine graph, look at its symmetry. So we want 0 to 360. However, our first solution isn't a valid one, but we can use it to find other valid solutions. So this graph starts at the bottom of a hill, and we walk lower down the hill backwards 30 degrees to get the first solution. So here we're going to do the same. To get lower down the hill, we're going to walk 30 degrees in that direction. So 180 plus 30 is 210. And again, we're at the bottom of the hill here. We're going to walk backwards like that, 30 degrees. So 360 take 30 is 330 degrees. So our solution's in order: x equals 90, 210, 270, and 330 degrees. So have a go looking through the worksheet. Be careful of anything on the worksheet that involves the functions sec, cosec, and cot, because we haven't covered those yet. That'll be next week's work. So next week we're going to go through reciprocal trig functions, which are the functions sec, cosec, and cot. So hopefully see you then.